Hello, ladies and gentlemen, and welcome back. We are on our second last question from the 2019 MMC paper. A child has 9 wooden blocks. 3 of them have the letter A painted on the side, 3 of them have a B, and 3 of them have a C. She is asked to use 5 of these blocks to make a 5-letter sequence, with the restriction, looks like the only restriction, being that no 2 A's can be consecutive. And they give us an example of a good sequence and one that is not so good because we've got 2 A's side by side. And we just want to know how many acceptable sequences are there. Okay, so how are we going to do this? Well, one way we could approach it is cases. I noticed the A's are a bit of an issue, right? So we can't have A's at all. So we might say, all right, well, how many acceptable sequences are there with no A's, or with 1 A, or with 2 A's? And 2 A's, we'd have to watch the placement of the A's, or 3 A's. In fact, for 3 A's, you'd have to sort of space them out like this, right? So that's one approach. Another thing we could do is make acceptable sequences of length 1, and then add on to them, make acceptable sequences of length 2, and then length 3, and then length 4, and then length 5. I don't know which one's going to be easier. This is going to involve sort of a lot of combinatorics and picking and choosing things and getting sequence orders just right. This method here is going to be a little tricky because there's only so many B's we can have, only so many C's, and we'd need to keep track of that. I don't know which one's best to try and go through. I think I'm going to try to build the sequences up. I think that might be something to start to try. If it turns out to be a hassle to keep track of, maybe we'll do some casework. But what can we do here? So let's think about sequences of length 1, length 2, 3, 4, and 5. 5 is the goal. Now we need to be careful that we never get 2 A's in a row. So I care about whether or not the last thing in my sequence is an A, or a B, or a C, I guess. All right, so how many sequences of length 1 end in an A that are acceptable? Well, only one. Same with the B's and with the C's. Okay. Now, how many sequences are there of length 2 that end in an A? Well, you could take any sequence that ends in a B and add on an A. That would be fine. One of those. Or any sequence that ends in a C and add on one of those. But you can't take the A and add on an A because then you'd get AA. And that's not allowed. How many sequences of length 2 end in a B? Well, we have enough B's to spare that any of these work. So you'll get 3 of them. Same with C's. Just take an AC, BC, or CC. There we go. That's kind of interesting. How many sequences of length 3 can you have that end in an A? Well, again, anything that ends in a B or a C will do the trick. 3 and 3. Just attack on an A to either of any of the sequences there. How about things that end in a B? Okay. Well, you could pick any of these and add on a B to the end. So 8 of them, 8 of them. Okay. And this isn't a problem. Now, one of these B sequences will be B, and then we added a B, and then we added a B. But remember, there are 3 B's, so that would be perfectly fine. All right, here's where I'm having to be sort of a little careful. Okay. How about sequences that end in an A that are acceptable and are of length 4? Well, really, just take anything except these. So 16 of them. Any of these 8 and any of these 8. Now, how about sequences that end in a B and are acceptable and of length 4? Well, take any of these sequences and add a B onto the end of them, so that should be 22. Except one of these sequences will be B, B, and B. So no more B's for you. So we got to subtract one of these off. So that'll actually be 21. Same with C. There's 22 sequences here, but one of them is CCC, and you can't add a C to that because the girl, I don't think she has a name, the girl only has 3 blocks with the letter C. So this is starting to become a bit of a challenge. And if it was 6 and 7, I might do casework. But I think we might be able to pull it out with 5, as long as we sort of reason our way out. All right, sequence of length 5 that end in an A. Well, any of these sequences can end in an A. Ooh. Have we used up too many A's? Now, if I'm putting an A at the end and it's an acceptable sequence, I can't have had 3 A's anywhere. So yeah, we have at most 2 A's in any of these acceptable sequences of length 4. So 42 of them here. Okay. How about the sequences that end in a B? So add them up again. 42 plus 16 should be 58. But how many of these would have 4 B's? That's a challenge. Maybe we should have altered our counting technique to count how many B's we have. That might be something worth looking at. So how many sequences of length 4 have 3 B's in them? Well, you could have BB, BA, or BBBC, or the A and the C could really be in any position. So there's 4 possible positions, 2 possible letters. Is it an A or a C? So that would be 8. So it'd be 58 minus 8 of these that already have all the B's you need. So 50. And same thing down here. So absolutely symmetric with C. And so in total, how many sequences of length 5? 142 is what I'm going to say. Now, I know it's a written contest, and I've more talked my way through that than wrote it out. But I think all you need to do is explain the chart you're doing. Very carefully explain why this is 21 and not 22, and why this is 50 and not 58, and you should be fine. Okay? Out of curiosity, let's take a look at the cases for question 9. For like the case-based way of doing question 9. So if I was going to do 0 A's, then I need to have only B's and C's. So I could have 3 B's and 2 C's, or I could have 2 B's and 3 C's. All right, a lot of some casework there. Now, how many ways are there to arrange 3 B's and 2 C's in a row of 5? So we could use a little bit of combinatorics. 5 choose 3 ways to place the B's, and then the remaining spots get C's. This is 10, and there's 5 choose 3 ways to arrange these as well. So if you've got 0 A's, there are 20 different possibilities. What if I have only 1 A? Well, there's 5 different places to put that A. 5 choices of where you put the A. And then you could have 3 B's and 1 C. You could have 3 C's and 1 B, or you could have 2 B's and 2 C's. Okay, and then you have to choose where to place things. So you could have 4 choose 3, or 4 choose 3 places to put. Choose the 3 places to put the C's. Once the A is in, you only have 4 spots left. Or 4 choose 2. So that's going to be 4 and 6. So 14 different ways times 5 should be 70. So 20 plus 70, that's 90 different possibilities so far, with 0 A's and 1 A. I'm going to skip over the 2A case because I think it's going to be a bit of a challenge. Now, if you had 3 A's, you don't have a choice as to where you can put these A's in order to make an acceptable sequence. It's got to alternate. So no choice there. You do have a choice. Do I have 2 B's? Do I have 2 C's, or do I have 1 B and 1 C? 2 choose 2, 2 choose 2. Of course, this is if you know choose notation. That's 1, 1, and 2. So 4 different ways. So now we're up to 94 in total. I'm going to D-box this 14, so when I'm counting at the end, I don't make a mistake. I should get the same 142. So where are we? We've got to make up about 50-something with these two A's. So if I only have two A's, it might be easier to count up all the different ways to do it with two A's without worrying about acceptable, and then subtract off the cases where the two A's are together. So if I have three B's, there's 5, choose 3, choose 2. I'm going to use multinomial notation here, actually. 5, choose 3 ways to put the B's in place and the A's, but some of those will have the A's together. So let's treat the A's as a single thing to place, and then there's only 1, 2, 3, 4 positions for choose the 3 B's and the 1 A blob. So that'll be 10 minus 4, 6. Or I could have 3 C's, same sort of deal. 6 there as well. Let's see, what else could we do? We could have 2 B's and 1 C, or 2 C's and 1 B. So that'd be 5, choose 2, choose the 1 C, and choose where the 2 A's go, minus 4, choose the 2 B's, the 1 C, and the 1 A blob. And then the same case repeated again. So I got 6, a 6. This is going to be, now we have to break it down into multinomial. So 5, 2, 1, 2. That's 5 factorial over 2 factorial, 1 factorial, 2 factorial. That's 120 divided by 4, 30. 4, 2, 1, 2. That's going to be 4 factorial over 2, 1, 2. Oh, no. One of those should be a 1. So that should be 24 over 2. So 12, 18. So we get this is 18 and this one's 18. So that adds up to 48 different cases. So we've got 20 plus 70 plus, I think it was 4. Yep. Plus 48. So that's 90 plus 52. And look at that, it's 142. So same thing. I think the case-based work would be easier for someone to write up. But I think constructing the sequence, I like doing this. Sometimes they'll do questions like these with permitted sequences and non-permitted sequences. And I like just sort of building things up. There was a good, I think it was a Cayley question on a Cayley contest, I want to say around 2000, maybe it was actually more recent. Maybe it was like 2018 or something like that, or 2016. And it had to do with a sequence of length 10 in which I think vowels couldn't be followed by vowels, and you couldn't have double letters in a row. And I like constructing sequences like this and finding the rules to make them. But yeah, got 142 either way. Both methods, I think, require a little explanation. As I said, if you wanted to go this route, explain what you're doing, like how you're making this, and your deductions as to why these two go here, but all 3 get to become here. It's because you have to be careful about A's followed by A's. And then explain why this isn't 22, it's actually 21. Explain why this isn't 58, it's 50. It's because you'd have to use all 4 B's in order to not place this B. So place the 4 B's, or place 3 of the B's, and then choose is the other one an A or a C. So those would be acceptable. And there we go. And then this one here, I think is easier to write up, a little more self-explanatory. No A's, 1 A. 3 A's not bad. 2 A's required a bit of work. I think if you don't know combinatorics, multinomial notation, binomial notation, this would have been a harder way for you to do 9. But I think that's two good ways to do 9. I like that. And 142. And actually, if you've got a third way to do question 9, I would absolutely love to read about it down below in the comments if you'd like to give me a brief description. But there we go, and on we move to question number 10. We'll finish off our Manitoba paper in the next video.